Good morning and assalamu alaikum, students. Uh, we have already started this topic, electric fields, and the topic that we have discussed so far deal with the force that one charge exerts on the other, and we have learned the expression that any two charges, let's say this is a charge, well, that we can denote by capital Q, and there is a relatively small charge nearby this charge, and let's denote it by small q. And we learned that the force that this charge exerts on this one, whether they are like charges or unlike charges, the magnitude of the force is always given by the expression F is equal to K Q Q over R square, where R is the separation between these two charges. If I assume that there is a field of this bigger charge, it's the region around it in which it has its influence over any charge that we brings into it, this force can be used to calculate the electric field strength exactly at this point where this charge small q is already located. So we learned that whether this charge is located here or not, this electric field, which is force per unit positive charge, it becomes K Q over R square. So this expression is known as the electric field strength at any point in the electric field where the force per unit positive charge is given by this expression. So if the force per unit positive charge F over Q at a position is known, we know the electric field strength there. So K Q over R square will always be the expression that we'll use to calculate electric field strength due to any charge capital Q. So this may be a proton, this may be an alpha particle, this may be any nucleus of gold, let's say, and if I know the distance from it, I can calculate how strong its field is from this charge, which is sometimes referred to as the source charge, and any charge that I bring in its field to test its strength is known as the test charge. So F over Q is simply the definition of electric field strength, force per unit positive charge. That is the definition of electric field strength. That of course is a variable and it depends on the position. So electric field is very strong when you come very close to the charge, and it weakens as you move away from it. So this is something that is often expressed with the help of graphs. And suppose this is a point charge and its electric field strength E is studied with its distance from R. So very close to it, when the distance is 0, we can see that theoretically that becomes infinitely large. So it goes like this. But as you come close to away from this charge, it drops to 0 value, and at infinitely large distance again, the value of Q, the value of electric field strength becomes 0. So this is the manner in which electric field, if I make it even more realistic, it should be a steeper fall because it varies inversely as square of the distance from the charge, as this expression indicates. So electric field strength, like force, obeys inverse square law. So just like the force reduces to 1/4 of its original value if we double the distance between the two charges. Similarly, electric field strength reduces to 1/4 of its original value if the distance is doubled. So if distance is made 3 times as much, the electric field strength reduces to 1/9 of its original value. So inverse square law is again at work here. Electric field strength is often calculated, and there are several questions in the exam. Let's calculate electric field strength at least for a couple of situations. Suppose we are required to calculate electric field strength of an alpha particle. This is an alpha particle, and I want to know what is the strength of the field when the distance is suppose 2 nanometer. So this is the distance 2 nanometer, and I want to know what is the field strength of this this charged particle if it happens to be an alpha particle. The alpha particle means there is the charge that it contains is known, because if you go to the data booklet, you know there are 2 protons. So K is 9 into 10 is power 9 into Q, which is 2 times 1.66 into 10 is power minus 19 coulomb, divided by 2 nanometer squared. 2 into 10 is power minus 9 whole square. So when you simplify this all, you get your electric field strength in Newton per coulomb. Usually the unit in which it is expressed is Newton per coulomb, but if you remember, there is one more unit, sometime convenient, that is volt per meter. So either in Newton per coulomb or volt per meter. In volt per meter, it is usually convenient when you have 2 parallel plates with the 2 different potentials applied, and there is certain separation in between. So uniform fields which can be created with the help of 2 parallel plates connected to battery. This is a more convenient unit to express because the potential difference is given in volts. Separation can be expressed in meters. But if it is a force per unit charge, clearly the charges are given, the forces are given, then Newton per coulomb, of course, is a more appropriate way to write as units. So this is a simple calculation. It could be something like 2,000, 3,000 or 4,000. Usually it's a large number because you have a very small distances involved here. This is large value. So even though this is small, you might have a large number here, something like 4,000 Newton per coulomb or even larger. So this is the formula. I write the formula again, KQ over R square, that we always use for this purpose, to calculate the electric field strength of any charge at any certain distance from it. So 2 nanometer could be 3 nanometer or 4 or 5. So obviously that value goes on decreasing as we go further away from it. One more structure that we study here, and the electric field strength is calculated for that, is also important, and let's discuss that as well. That is a sphere which is hollow from inside, and it is conducting sphere, and there is some charge that you spread on it. And since it is a conducting surface, this charge is evenly distributed on it. Let's say this charge is not known, but due to the presence of this charge, we have an electric field strength on the surface of it. And interestingly, this electric field strength is given by the same formula, because the charge that we spread on the surface of a conducting sphere uh, behaves as if all this charge is concentrated at the center. So it's not different from the picture that I have drawn already, with a charge centered here and its field lines made like this. So all this charge is actually concentrated here. It behaves like that. So all that charge can be assumed to be concentrated here, and this can be written as Q. So let's find this value of Q, assuming that we know the value of the electric field strength here at the surface. So E, if it is something like 4,000 Newton per Coulomb, let's say, and this radius of the sphere is known, and that is assumed to be 12, let's say this is 12 nanometer. Let me check what I have written here. 12 nanometer is too small. Let me make it a more realistic value. 12 centimeters. So this is a reasonably large sphere, 12 centimeter its radius, and the electric field strength at the surface is 4,000 Newton per Coulomb. That is already known. The question is, what is the charge which creates this much of electric field strength, 4,000 Newton per Coulomb, when the radius is 12 centimeters? So simply you use this expression with E equal to 4,000 equal to K, which is 9 into 10 is power 9, Q over radius, 12 into 10 is power minus 2, which is meter squared. When you simplify this all, of course a simple calculation with the help of calculator, you see this Q comes out to be, I have done this calculation, and it comes out to be 6.4 nano coulomb. So this is the typical of the size of the charge that we use to create this type of electric fields. 6.4 nano coulomb positive charge is given to the surface of a conducting sphere, and as a result of this charge given to this surface, this charge behaves as if it is concentrated at the center, so it creates a certain electric field strength at the surface of the charge itself. So we use the same formula that we originally used for a point charge at a distance of which we take this electric field, which is basically the surface of this conducting sphere, and the distance here is the radius of it. So the idea is that there is no difference between a charge considered a point charge somewhere in the space, and you are calculating the electric field strength around it at any given distance, or a sphere with that same charge spread uniformly on its surface. That same charge behaves as if it is concentrated like the charge we considered earlier as a point charge located somewhere. So this sphere, which is charged, has this charge on it, and due to this charge we have the electric field strength. The next thing is how does the electric field strength of this conducting sphere varies as we move from its center to its surface and further away from it. There are many questions about that. Let's discuss that. Suppose this is the axis that we use to describe the variation of electric field strength with the distance r from its center. The important thing to remember is that if this is the radius, this distance is exactly the radius of this sphere. What is the shape of the electric field strength when we move from its center to its surface. You will always remember that for conducting sphere, this is a conducting sphere. A conducting sphere, and it always has zero electric field inside it. There is no charge inside, it's hollow, and you have given this charge on the surface of it. So there is no charge inside, no electric field inside. This charge behaves as if it is concentrated here. So electric field, if I assume all this charge at the center, the electric field has its direction on all sides. So for each component of electric field on this side, it has an equal and opposite on this side. So electric field strength overall is zero inside the conducting sphere. But at the surface of it, it rises to that maximum value that depends on the amount of charge you give it. Let's assume this is the maximum value here, and we denote it by E naught. But as you move further away from it, if this is the radius of it, and this is 2 times the radius, this is 3 times the radius, this is 4 times the radius, it drops in this manner. So this is same 1 over r square. So when you make 2 times the distance, it drops to half of its value. When you make 3 times the radius, it drops to 1/9 of its value. So a steep fall is observed, and even steeper, it is something like this. So this is a steep fall due to inverse square law at work here. So important thing that you will remember here is electric field strength inside a conducting sphere is taken 0 because there is no free charges inside, and even if this charge is assumed to be concentrated at the center, electric field is equal and opposite in all directions, so the net effect is 0. So it's the cancellation basically, due to which the electric field inside is always taken 0. But as soon as you come at the surface, it rises to that maximum value. But when you move further away from the surface, it drops in this manner, like it drops in the case of a point charge in anywhere in the space. So this is how the electric field changes. But what if there are 2-point charges placed side by side? That is also useful to study. Let's say we have two charges placed side by side. How does the electric field in the space in between these two charges vary? That of course depends on the signs of these two charges. Let's assume both of them are positive charges, and for the sake of simplicity, we assume that they have exactly the same magnitude. If they have exactly the same magnitude, these are the lines where the electric field can be assumed to start. I mean, this is exactly the point where this charge is located, and this is the point where this charge is located. When I start from this point charge to this one, the electric field of this charge, which is initially very large because we have already seen that theoretically it is infinite, add that charge. So it starts from a very large value, theoretically infinite, and it drops in this manner. And it gets like this, almost touching it, but theoretically at infinite distance it should touch it. So no need to touch this line, just make it as close as possible and then leave it. What happens to this one? Because this is also positive, its sign will be negative because the direction of the electric field will be opposite. The electric field of this charge will be in this direction and electric field of this will be opposite. So electric field of this will be exactly of this shape but in the opposite direction. So an identical electric field due to this charge, if they are exactly same in magnitude, in the middle the two charges are exactly equal and opposite. See, it is a positive charge, but it's a positive electric field because its direction is this. This is negative electric field because its direction is opposite. So if these two are exactly same and opposite, they cancel exactly here. So if I draw the net charge of the two, net electric field, it looks like this, in this manner. So net electric field is this broken line, which means this one, which passes through 0 somewhere in the center, because these two are exactly equal in magnitude, opposite in sign. I mean electric fields. Electric fields are exactly equal here, opposite in sign because the two are opposite in direction. So they cancel each other. So electric field is exactly 0 here. Sometimes we are not sure where the electric field is 0 and we have to do some calculation. Let's discuss one such question where we know the two charges, they are given, and at a certain location we know the two charges cancel each other's electric field, but exactly what is that distance from one charge, that is interesting. And let's discuss, because we have questions like that in the exam. Suppose we have suppose this is this charge is slightly larger in magnitude and positive, of course, and it is a gold nucleus, AU, and we know that a gold nucleus has 79 protons in it. That means the charge on it is 79 times the elementary charge. So a positive charge 79 times the elementary charge. And let's say this is a relatively smaller charge, an alpha particle, and this alpha particle, which is He, and it has 2 protons. So this is a positive charge with 2 elementary charges. We know the amount of elementary charge, we can take it from the data booklet. The question is, where exactly the two electric fields cancel each other? We did this question, a similar question in gravitation as well, where we knew that they exert a force on each other. The field is inward in that case, but there as well the field was opposite and it cancelled at one point, and we equated the fields there, and by cancelling we knew that at a certain distance from the earth or from the sun the field is 0. So we are going to have a similar exercise here. Suppose this is the point. This is the point where the electric fields become equal. They are opposite already, and where they become exactly equal is a distance x from this gold nucleus. So this is distance x. If I know the total distance already, let's say the total distance is 10 micrometer between the two charges. So if this is x, this remaining distance is 10 micrometer minus x. So this is now the distance expressed in meters. The total is 10 micrometer, and at a distance x from the gold nucleus, the field is 0. And the whole exercise is to calculate the value of x. Of course, the starting point is that electric field strength due to this is given by k q over x square. And when it is algebraically added to the electric field due to this, this is minus k q over 10 micrometer minus x whole square. This must be equal to 0. Because the two fields are adding up there, and if I take care of the two as vectors, one has to be negative and one positive, so the two should add up to give 0 there. As a result, this goes to the other side. Due to this negative sign, it becomes positive, and this k gets cancelled, and it's easy to see that it will become q over small q is equal to x square over 10 micrometer minus x. This is whole square. And if I remove the square from here, and this q is taken 79e, this q is taken 2e, these two get cancelled, and I take the under root because I have removed the square from this side. This is now a very simple algebraic equation, and it simplifies to x is equal to, as I have done this calculation, it shows that it is 8.6 micrometer. That means that if the total distance is 10 micrometer, at a very large distance from this gold nucleus, 8.6 is very close to this small charge. And that makes sense because the electric field strength of this is very large. So it is at a very large distance from it that the two fields become equal and opposite and cancel each other. So at 8.6 micrometer from this gold nucleus, the two become equal and cancel. So if they ask us to draw what is this variation appears to be on the graph without making any scale, this will be the manner in which it changes. Roughly, this is the shape of the graph. So basically, this is the distance from this is 8.6 up to this, and the remaining add up to make it 10 micrometer, because the total distance is 10 micrometer. So 8.6 is this, and the remaining 1.4 micrometer. So the total becomes, so this is that part of the graph where the electric field of this is stronger, but as it becomes away, we move away from this charge, the field becomes weaker and weaker. And this is the point where it becomes so weak that it becomes equal and opposite to the electric field of alpha particle, and that is the point where the field becomes 0. And as we move further away from it, this field, which is opposite in direction, that starts becoming significant, dominant, and that is why the curve goes to this side. And it can be easily seen that by the time we reach 10 micrometer, the field is very, very large, and that is entirely due to the alpha particle. So this is how the electric field varies. But what happens if the two charges are opposite in sign? That's the last point of our discussion. Let's say this is a charge Q and we have another charge roughly the same magnitude, but it is opposite in sign. What will be the shape of the electric field strength, the overall electric field strength, not individual, as we move from this to this? So this is the distance x from this one. Let's say we are at point P somewhere, and this is the distance x we have moved so far, and as we move further away from it until this, what will be the shape of this graph if we are studying the variation of electric field strength? This time, if we start here, the electric field strength is very large as always. It drops to a very small value as we go to a point here, but it does not go to zero. And as we move further away from it and close to this, the electric field starts increasing again, and it's a shape like this. Now, this is easy to understand because this time, let's say this is the position of it. So if I make it inaccurate due to position, it should be something like this. So this is the line where the charge is located. So when you move from this charge to the center, the electric field becomes weaker as expected, because as you move away from a charge, the field becomes weaker and weaker. But beyond that center, somewhere in the middle, you move to the right, the electric field starts becoming large again, because the field lines are like this now. Instead of cancelling, they reinforce each other, only becoming weaker at the center, but they are very strong here. The field is very strong here. So when we plot a graph, it has a dip here, it has a lowest point here, but as you move further away, the field becomes strong again and close to that point again. If this is the position showing that charge, this minus q, the field again becomes very large, theoretically infinite. So it's a cup-shaped curve that we get now. This is the shape of the graph that is always results due to two charges which have opposite signs. If they are nearly same magnitude, you have this dip at the center, that is understandable. And if one of these two charges, let's say this charge is very weak in magnitude, this dip will be very further away from it. Let's say this is very, very small in magnitude. I make it minus small q. So the change that will take place in this graph is that you have a shape in this manner, like this. So this is the shape of the graph. So this is it for today. Today I'm not giving you any worksheets. You go through the theory that we have discussed, try to make sense of it, try a few questions on your own, but I'll share with you many questions before I start the next class. You will have a worksheet, so you have many questions to attempt and discuss. Thank you for today.